Coherent control of light-matter interactions in a semiconductor nanophotonic device will be given by Edo Waks from here, from more or less here, the University of Maryland in College Park.
Okay. How do I do this? Do you know how this works?
It works already.
Everybody can hear me? Okay, thank you. Okay. Everybody in the back can hear me? Good. I'll take that as a yes. I want to thank the conference organizers for inviting me. It's a real pleasure to be here today and talk to this community. A lot of the work that we do in my group and in my field is really been inspired by and in many ways follows in the footsteps of a lot of the great stuff that has been done in atomic physics. So I hope that you'll find, I hope to convince you that semiconductor, quantum dots, and nanophotonic devices are a really interesting platform to study some of this physics that has been under development for quite a while. So our research is really motivated by two fundamental questions. One is, can we create strong interactions between a single atom and a single photon? And I think thanks to a lot of advances in both atomic physics and semiconductor photonics, the answer to this is becoming pretty clear that too much. Take off my badge. Sorry about that. That rumbling was probably disturbing everybody. So I think the answer to this question is pretty clear that this is indeed possible. The second question, which is arguably a little more difficult to address, is can we actually control these interactions in a meaningful way? And I think that I don't have to belabor the point to this community that if we could control interactions between single atoms and single photons, there's a lot of fantastic things that we could, in principle, try to do. There's a lot of fascinating work on quantum networks, distributed quantum computation, and you've seen at least elements of this in many of the previous talks. So in this talk, I'm going to give you two examples of coherent control between a single atom and a single photon. The first example is basically a quantum logic operation on a photon using a single atom. And in the second example, I'll talk about how we can use an atom coupled to a cavity to coherently control vacuum Rabi oscillations. And I'll describe that in a little more detail. However, I want to start off by pointing out that we don't use real atoms in my group. True to the title of this session, we use artificial atoms called quantum dots. Specifically, we use indium arsenide quantum dots. This is an atomic force microscope image of a sample that contains indium arsenide quantum dots. Each one of these little specks is an indium arsenide nanocrystal about 20 nanometers in diameter and about 5 nanometers in height. And it's embedded inside of a gallium arsenide semiconductor material. And due to the fortuitous band alignment between indium arsenide and gallium arsenide, an electron or hole trapped in the indium arsenide region cannot easily escape into the gallium arsenide because of the band alignment. Both electrons and holes are confined, and they're confined to a sufficiently small dimension that they occupy discrete energy levels. And if we optically isolate one of these discrete energy levels, then we can start to think about this nanocrystal as effectively a two-level atom. What are some of the evidence for the behavior of the atomic nature of these kind of nanostructures? Well, first of all, we can just look at their fluorescent spectrum. And unlike a bulk semiconductor spectrum, what you see from these quantum dots is these very sharp resonances which correspond to these energy levels. More specific, this is a nice start, but it doesn't prove that these are really atomic two-level atom systems. Maybe a more strong evidence is by looking at the photon statistics coming out of the dots. If we look at the probability of two photon events, we see that it's basically periodic. As a function of time delay between the photons, we see this periodic pattern, which is due to the fact that the photons are being produced in a periodic pattern separated by 13 nanoseconds. But at time 0, there's no probability of seeing two photons at the same time. This is because this is basically a single photon emitter. So why do we like to study quantum dots as opposed to real atoms? Well, one of the nice things is that this is a robust quantum emitter. So we can study the same dot for months and months and months. It has a lot of good qubit candidates, for example, bright excitons, spin, dark excitons. I'll touch on some of these points. But most importantly for us, these dots are easy to localize and to couple to other photonic structures. So instead of having to use very complex atom traps, our artificial atoms are already embedded in a semiconductor matrix. And a nice feature of this is that this embedding semiconductor, it's a high dielectric material. Gallium arsenide has an index of refraction of 3.6. So simply by patterning the surrounding dielectric material, we can make photonic structures. For example, we can make optical cavities, and then we have a natural, we've created a device where a quantum dot is embedded in, or a single atomic system, a quantum dot is embedded inside a photonic cavity, and we can start to study cavity atom interactions. So the main reason why one would want to put a dot in a cavity is, of course, to more strongly interact light with the atoms. The cavity will store the photon field for hopefully a reasonably long amount of time so that you can get a significant absorption by the dot. Whenever you put any kind of atomic system into a cavity, there's 3 important parameters that will dictate the kind of interaction you're going to get. There's the cavity quantum dot coupling, which is the coherent reversible interaction between the atom, the photon field and the 2-level atomic system. And then there's 2 other parameters which describe the effect of the environment in decohering your system. One is probably the most important effect is the cavity field decay rate. Another important effect is the dipole decay rate. And depending on the ratio of these 3 parameters, you're going to get different types of interactions. We are particularly interested in the so-called strong coupling regime, where the coupling strength is greater than all of the decoherences in such a way that if you excite the dot, it will emit a photon into the cavity and reabsorb it and re-emit it coherently. We observe what one would refer to as vacuum Rabi oscillations. We heard a little bit about this this morning from the talk by Serge Haroche. The idea is that in this regime, the excitation of the dot and cavity will oscillate in time. It will also eventually damp out due to damping mechanisms, but hopefully we can get a decent number of coherent oscillations before we lose the coherence of our system. In the frequency domain, what this looks like is basically a splitting of the cavity and quantum dot emission into 2 coupled states called polaritons, where the splitting between these 2 polaritons is simply twice the vacuum Rabi frequency. And so this is basically complementary pictures of this strong coupling regime. So in order to get the strong coupling regime, we realized that the coupling strength between the dot and the cavity is inversely proportional to the square root of the mode volume, while the cavity decay rate is inversely proportional to the cavity Q. So in order to reach this regime, we need cavities with small mode volumes and high Qs. And in our group, we use photonic crystal cavities. These are made by patterning a periodic array of air holes into the gallium arsenide slab. So this periodic this 2-dimensional pattern creates a photonic crystal. And we introduce a defect into this crystal by simply removing 3 of these holes. And here's a close-up of the defect region. If you took a slice of this in 2 dimensions and looked through the cross-section, this is what you would see. It's basically a suspended membrane with air on top and bottom. And the reason why we do this is we use a total internal reflection in the 3rd dimension to confine the photon. But in the plane, it's 2-dimensional Bragg reflection that keeps the photon confined in this defect region. If you simply simulate numerically the cavity mode pattern, you see that the field is very highly localized within the cavity, within the defect region. This is on the order of a micron or less. So we're really confining the light to within something on the order of a cubic wavelength. And we can do this with pretty high Qs. This is a particular cavity that we made, had a Q of 31,000. At longer wavelengths, people have gotten Qs into the hundreds of thousands. So one way that in order to demonstrate that we can actually attain the strong coupling regime, one of the easiest ways to show this is just to look at what the reflection spectrum of the cavity is. So we just reflect light off the cavity. We have to take some precautions to make sure that the reflection off the surface doesn't blind our detectors, but we know how to do this pretty well. And we simply tune the laser across the cavity. And this is what we see when we make this measurement. This bright line, first of all, here I'm measuring wavelength versus temperature. And this bright line here, that's the cavity spectrum. And you can see that as the temperature goes up, it seems like something crosses through it and slices it in half. This is actually a quantum dot that is being tuned through the cavity. As we increase the temperature, we shift the band gap of the semiconductor material, and that redshifts the quantum dot across the cavity resonance. And this anti-crossing is the evidence that we're in the strong coupling regime. And if we simply take the spectrum on resonance, we see this very nice, what happened here? There. Very nice sharp doublet with that shows a very good strongly coupled spectrum. And so, of course, we can now control the coupling between the quantum dot and the cavity by simply changing the temperature and tuning the quantum dot in and out of resonance. But that's a very slow process. It happens on the order of seconds. So the question is, can we coherently control this? Can we control the interaction between the dot and the cavity on timescales that are short compared to the decoherence time of the quantum dot? And to do that, we have to stop thinking about the quantum dot as a two-level atomic system, because we need more levels. We're going to need more energy levels in order to achieve this coherent control. So the first thing I'd like to point out is that the quantum dot exciton is not just one level. There's actually 4 possible excitons you can form, and that's because an excitation in a quantum dot is composed of an electron and a hole, and the electron has plus minus 1/2 spin, and the hole has a plus minus 3/2 spin, so there's 4 possible spin combinations for the electron and hole to occupy. 2 of these combinations, where both the electron and the hole point in the same direction, they have an angular momentum of plus minus 2. So these transitions are not optically active, so we don't really see them. The other 2, however, are so-called bright excitons. They are optically active. They can absorb and emit light, but we don't normally see them because they're degenerate or nearly degenerate. So if you look at the spectrum, you just see one line. However, if you apply a magnetic field, you can intentionally break this degeneracy. And then, we've done this. We've built a setup where you can apply magnetic fields up to 9 Tesla. And if we just look at the spectrum of a dot as a function of magnetic field, you see that it splits into these two branches corresponding to the 2 bright exciton states. Now consider the following scenario. Let's suppose I have a dot in a cavity, and I apply a magnetic field, and I apply just the right magnetic field to tune one of these transitions onto resonance with a dot, while detuning the other transition far off resonance. Here's an example of how that looks like. We have a dot right here. It's a little bit hard to see on this projector, but there's a resonance here. And at about 2.6 Tesla, we've tuned one branch onto cavity resonance. The other branch is over here. And this anti-crossing shows you that the dot, the bright exciton branch of the dot is strongly coupled. And so if we look at the level structure under this condition, we have a really interesting system where we effectively have a qubit, 2-level system, coupled to the cavity with a 3rd transition, which can serve as a strong interface to a photon. So we basically have a qubit in a cavity system, and this other branch, where the ground state maybe is qubit state 0, this minus state is qubit state 1, and then we have this 3rd state that can serve as a qubit photon interface. And the reason why this transition is, the way this interface works is by exploiting the fact that the cavity reflectivity will strongly be determined by by the coupling strength to the dot. So if you look at the reflection of the coefficient of the cavity on resonance, it is a strong function of this parameter called the atomic cooperativity, which is proportional to the square of the cavity quantum dot coupling strength. So if the quantum dot is in the ground state, it can now make an optical transition to this to the plus state, which is resonant with the cavity. So the atomic cooperativity in the strong coupling regime is expected to be large. It's expected to be a number bigger than 1. In which case, the reflection coefficient is a positive number. So a photon that reflects off the cavity will reflect with no phase shift. If, however, we use coherent optical control to just move the population to the excited state, then cooperativity goes to 0 because we've effectively decoupled the dot from the cavity. And now the photon reflecting off the cavity actually experiences a pi phase shift. So in the parlance of quantum information processing, this is a quantum dot photon controlled phase gate. It allows us to actually control the phase of the reflected photon by the qubit state of the dot. What we implemented is not exactly this kind of a gate. We implemented a closed variant. We exploit the fact that the cavity has a well-defined polarization direction, and that polarization direction points orthogonal to the direction of the Rove defect. So you see in this direction, the Rove defect points in this direction, the polarization is along the x direction. And so if we rotate the polarization of a photon 45 degrees to the cavity polarization axis, only this component will couple to the cavity. Now, if the quantum dot is in its plus state and the cooperativity is 0, this component will experience a pi phase shift. It will rotate across the, it will be reflected across the origin. And so what will happen is the polarization will rotate 90 degrees. If, on the other hand, we're in the ground state where the dot, where now there's no phase shift off reflection, this component will remain aligned in the same direction. The polarization of the photon will not reflect. So effectively, by exploiting the polarization of the cavity, we convert this phase gate into a quantum dot photon controlled NOT gate. And this controlled NOT gate plays an important role in many quantum information applications. You can use it to distribute entanglement. You can use it to construct quantum networks. You can do non-destructive quantum measurements and also photon-photon interactions. But these are all, we're not this ambitious yet. We would just like to demonstrate this gate. And so we did this by simply using a pulsed laser excitation. We use a pulsed pump to control, to set the quantum state of the qubit. Then we reflect a probe pulse off of the cavity on resonance with the cavity mode. This is what we see when we look at the reflectivity as a function of pump power. We see that the cavity reflection spectrum oscillates. This is due to the Rabi oscillation of the qubit through the excited state. We can also map out the entire cavity reflection spectrum just by tuning the probe across frequency across the cavity. And here we show the measured cavity spectrum at these 4 different points, at the pi, 2 pi, and 3 pi pulse. So this is the case where there's no pump. And here the quantum dot is in its ground state, so the cavity spectrum looks like it has a dot strongly coupled to it. When we look at the pi pulse condition, that's the blue curve here, it now looks like a bare cavity reflection spectrum because we've moved the population to the minus state, now it's decoupled. And similarly, with 2 pi, we get back the strongly coupled spectrum. And again, we get, at 3 pi, we get back this bare cavity spectrum. So we can actually coherently control the entire cavity reflection spectrum using this qubit state. The gate, we can ask what the gate fidelity is. We do this by measuring in all the different polarization directions and all different combinations of input and output polarizations. When the quantum dot is in a minus state, the gate fidelity is actually very high. It's above 92%. When it's in the ground state, the gate fidelity is not as good. The reason is because our cooperativity is not large enough, and also due to the finite bandwidth of our pulse, which is now no longer, you get perfect fidelity only for an infinitesimally narrow spectrum. But if you just basically use these fidelities to estimate what kind of an entanglement fidelity you would get if you try to use this gate to do an entanglement, you estimate that we should be able to get an entanglement fidelity of about 0.8. We haven't demonstrated that yet, but it does show some promise for doing these kind of entanglement distribution experiments. So now I want to change gears a little bit. That was one example of how to do coherent control. Now I want to go back to think about the dot again as a 2-level system. So I'm not going to apply any magnetic, we're not going to apply any magnetic fields. We're going to treat the quantum dot as just a ground and excited state. Suppose that the quantum dot is initially detuned from the cavity mode by a large amount. If we excite the dot, it won't transfer any energy to the cavity because it's largely detuned. However, suppose we can very quickly, and here quick is on the time scale of the vacuum Rabi frequency, tune the dot onto the cavity resonance. In this case, now the dot will couple to the cavity and transfer energy, and then we tune it away very quickly again. This allows us to coherently transfer an excitation from the quantum dot to the cavity mode. And we can, in principle, do this multiple times. We can create, we can excite the dot again and feed more and more and more photons. We can actually create arbitrary superpositions of light matter. And this is a technique that has been demonstrated extensively at microwave frequencies. You've heard this morning again from the Harosh group. This is one of the this was demonstrated a long time ago. Particularly promising results have been shown in using circuit QED, where the strong coupling parameters are really, really good. But at optical frequencies, it's much more difficult. And that's because we're facing a couple of challenges. One is we're facing much faster decay times. And the second is also we're also have a larger G. So we have to do these tunings on the order of picosecond to nanosecond timescales. So how do we do that? Well, a while ago we showed that a cavity can implement a very large AC Stark effect. So here we are tuning a laser, and this is a cavity resonance. As we tune the laser and we hit the cavity resonance, you see two quantum dots here. And once the laser hits the cavity resonance, the quantum dots shift away from the cavity. This is an AC Stark shift. So it allows us to tune the dot frequency optically. And the speed can be very fast. It's limited only by the cavity lifetime, which is on the order of 5 picoseconds. But there's a problem. The Stark shift will only tune you away from the laser frequency. So if we want to actually tune the dot onto the cavity and also use the cavity to enhance the AC Stark effect, this doesn't work. We need to be able to, we need to somehow be able to tune the dot into the cavity mode. And so there's an interest, we developed an interesting solution to this problem. We exploit the fact that we're working with a nanophotonic system that allows for device integration. So here we can actually couple two cavities very easily to each other. We simply create two cavities that are sufficiently close such that a photon in one cavity can tunnel back and forth between these two cavities. And if we look at the new modes of the system, if this tunneling rate is fast compared to the decay time, what will happen is you'll create two new modes of the system, which are symmetric and anti-symmetric modes of the double cavity. Oh, I did it again. Of the double cavity system. We call this a photonic molecule. And these modes are analogous to the modes, if you had two coupled harmonic oscillators and you coupled them by a spring, these would be the common and stretch modes of the system. And these detuning between these modes is simply given by the tunneling rate of the photon between the two cavities. So if you look at the spectrum of this type of photonic molecule, we now have two modes. We have one over here and another one over here. And this sharp line is a quantum dot. And so as we tune the temperature now, we see that the quantum dot will anti-cross with this sharp line, with this second mode. So now we can have strong coupling in this mode, and we can use this second mode to do an AC Stark shift. So the first thing we can try to do in the system is we can, to show that we can actually Stark shift the dot, we simply tune the laser across this mode, and we look at the emission of the quantum dot, and you can see that as the laser hits the resonance of this mode, the dot shifts and starts to couple to the cavity. You can see that there's already some energy transfer between the dot and the cavity occurring. We can also tune the laser across the other mode of the cavity. Now we see the dot shift the other direction. Here there's more noise because the laser is much more closely tuned to the spectrum, so we get more scattering. So this shows that the dot is not coupled to both of these modes. And the first thing we can do using the system is try to excite the cavity, load it with a photon, then use the second mode to tune the dot onto the cavity, and then transfer excitation to the dot. And this is shown in this figure. This plots the spectrum as a function of the delay between the excitation and Stark pulse. And you can see that at near zero delay, we get a very clear transfer of energy between the cavity and the quantum dot. We can compare this to numerical simulations, and we see that we have very good agreement between with the predicted behavior and the measured behavior, where the transfer is going from the cavity photon to the dot. We can do the reverse. We can excite the dot, put it into the excited state, and now transfer its excitation to the cavity. And this is what we observe when we do the reverse process. Here, we're now pumping the quantum dot, so it looks bright, and then the cavity resonance is over here. And you can see that at positive pump probe delay, we transfer energy to the cavity. This is a integration of the cavity pixel, the pixel corresponding to the cavity resonant frequency. And it has this oscillatory behavior. This oscillatory behavior, it's a little complicated to explain, but it's expected. It's due to a perturbed free induction decay caused by the fact that we're tuning the dot onto the cavity resonance before it has had time to decay. And that gives this kind of sinusoidal behavior, which is also seen in the numerical simulations. So we can also look at the power dependence. If we increase the power, we increase the detuning between the dot and the cavity, and that increases the vacuum Rabi frequency. So we expect to see the signature of vacuum Rabi oscillations, which is indeed observed as we look at the fluorescent spectrum of the cavity, the emission spectrum of the cavity as a function of pump power. Again, fully consistent with the simulations. So this is the first evidence that we're not just incoherently exchanging energy between the dot and the cavity, we're actually coherently transferring the energy. Maybe a stronger evidence of coherent transfer is by performing something we call polariton-Ramsey interference. Here, we tune the dot onto resonance with the cavity so that our modes are now the two polariton states. We excite these two states with a very fast pulse whose spectrum overlaps both polaritons. The block picture is probably a very useful picture for trying to understand what's happening here. When we coherently pump, this is a two-level system. If we draw a block sphere where the lower and upper polaritons are the equator of the sphere, then because we're creating a superposition, we're effectively creating a state along the equator of the block sphere. We then wait for some fixed amount of time, in which case the block vector will rotate along the equator of the sphere, and then we mix the two states using a second Stark pulse, and that will rotate the block vector either towards the upper polariton or the lower polariton. In order to understand why this pulse actually mixes the two polariton states, maybe the easiest way to explain this is to realize that if you draw the level structure in the uncoupled basis, where we have a off-resonant laser pulse that's creating a Stark shift on the dot, this is equivalent in the polariton basis to basically a pulsed Raman transition with an effective Rabi frequency of 2 omega squared over delta. And so here's the measurement of the polariton-Ramsey interference. We're plotting the spectrum as a function of pump probe delay. And we see here the pump is happening before the probe. These two pulses are our polaritons. And if we plot the intensity of the polaritons, we see that there's this anti-correlated oscillation. The upper and lower polaritons are oscillating out of phase. And again, this is very consistent with the predicted behavior. It, of course, dies out very quickly due to the finite cavity lifetime, but we can clearly see at least one oscillation. So in summary, I've shown you two examples of how to achieve coherent control in a strongly coupled atom cavity system. One is a quantum logic gate, and the other is by directly controlling the vacuum Rabi oscillations in the time domain. And in the last remaining seconds that I have, I want to acknowledge all the people who really did this work, my research group, with my graduate students, postdocs, and also Glenn Solomon at NIST, who grows all of our wafers. And with that, I want to thank you for your attention.
Thank you very much. We have time for some short questions. Bill.
So you mentioned at the beginning, and it comes up again and again, that you've got a reasonably high Q, but you'd love for it to be higher in these photonic crystal cavities. So what is it that limits the Q? Are we talking about material losses? Is there leakage of the field into other modes, or what's going on? And what's the prospects for making that better?
In our case, it's probably material losses. At longer wavelengths, the Qs can be 10, 20 times larger, but we are working close to the band gap, too close to the band gap of gallium arsenide. So that's the real key to getting higher Qs is to go to longer wavelengths.
Okay, I see there are not any questions. I have a very short question myself. I always see that in the semiconductor community, you always scan the power of the exciting pulse to go for the pi/2 and so pulses. There is no system that could give you the ability to tune the time of the pulse instead, which we prefer usually in quantum optics or so.
Yeah, I think that's a good point because when we do these experiments, we're typically using a few picosecond pulses, and so we're limited by whatever pulse our laser produces. It's possible to try to use an electro-optic lithium niobate modulator to make these pi pulses, and I think that there's been some work to do that, and I think that would be a very valuable thing to do, but it's very difficult to make a pulse that way of 5-6 picoseconds. So in this particular system, it would be tough to use.
Okay, thank you very much. And let me